I would like to introduce you today to the VS-1 system. It's a system that I came up with in 2004. It is a new kit of parts to solve curtain wall facade problems on any kind of building. I will be focusing today on multi-story buildings. The idea, when I had the idea, I was working in a custom environment. I had another company before, Innovation Glass, and we operated in the United States, and we did one-of-a-kind structures. I wanted to share with you some of the projects that led up to having the idea. These are some of the projects. On the left is the first tension truss structure built in the United States after the Louvre Pyramid was built in 1991. First cable net in Chicago in 2001, and a hyperbolic paraboloid surface cable net in Washington, D.C. This is Time Warner Center in Manhattan, which was, at the time it was built in 2001, the largest spanning cable net in the world. On the right is an all-glass structure where the walls are glass, the beams are glass, and the stair treads are glass. It's in Times Square in New York City. This is a collaboration with IMPay in Boston. Boston Federal Courthouse is a stressed shell structure spanning 100 feet. It's only 10-inch structural depth. Cast glass sculpture fountain in Chicago. It's 50 feet high, and it needed some structural engineering to hold it up. It was an artist's project. And this is a world's largest cable net. It's in Beijing. It's the Central Bank of China's main office. And all of that work led to this idea, the VS-1. This is the kit of parts. It's very simple. It's the question was asked in 2004 by my team. What does a curtain wall want to be? What does it need to be in the modern sense? What are the modern, the current architectural, what is the current architectural community asking of facade systems? And it's different than in 1950 when the original idea of the curtain wall that we all use around the world was developed. Oil was $10 a barrel in 1950, and now it's, it fluctuates up to $100 a barrel. So it's a different world. We endeavored to respond to those questions, and I'll run you through what you get when out of a solution when you use the VS-1 system. We've eliminated the horizontals. There are none in our system, so we've eliminated 50% of the metal in the facade solution, and it allows you then to have very minimalistic, simple solutions at the boundary conditions. Our standard shape is not a box. It's in a highly engineered minimal blade, which makes the VS-1 system very transparent. It's a point-supported system, so you see the glasses pulled away from the mullion by about 50 millimeters, and it really expresses the glass plane as a plane as opposed to a aluminum wall with glass. We have a zero sightline window system that's part of the facade program. We are very, very focused on the sustainability. In the United States, our aluminum extrusions have almost a 75% recycled content. Long spans, we're able to go up to 14 meters without the need for an intermediate steel beam. We have very strong thermal performances, superior to unitized walls. The system is reversible. You're able to put the mullions to the exterior. So if your architect or you as a designer wish to express a vertical element to the building, you essentially can get it at no charge by putting the mullions to the exterior. Faceted facades, the VS-1 system solves facades like this readily without any modification. There's a movement in architecture today all over the world for very large glass. I just came back from a show in Germany, and the largest panel of glass that you can buy today is 10 feet by 66 feet, a single piece of glass. And because the mullion is so slender, the VS-1 walls, when they are finished, are very, very thin, very transparent. The structure does not jump out at you. Should your program call for very intense geometry, let me see if I can. Thank you. The system responds extremely well to highly complicated geometric surfaces. This is a University of Chicago arts wing building. It's in a Gothic environment. The rest of the campus is Gothic in architectural style, and the architect brought this building in. We are not limited to just having a single cladding element in the system. If your program calls to have multiple materials, multiple thicknesses, we can accommodate that. We've done several projects with highly automated buildings trying to optimize the thermal performance with a computer control system. Because the system doesn't have any horizontals, you as an architect can really start to be more creative without incurring excessive costs. So this wall, for instance, is a quilted sawtooth wall, and the cost of making this wall compared to a flat one is minimal. You're essentially paying for a little extra square footage of glass, but the impact on the metal system was zero as compared to a flat wall. One of the features of the system is that if you can upgrade it 5 years, 10 years down the road, the system allows you to attach elements. If you have a tenant change and the tenant wishes to put a sign on, or if you say, I want to now install photovoltaic panels on the outside of the facade, you can do that 5 years later with the facade fully intact without removing your tenants. When you go multi-story, of course, the fire separation is a critical element. We have many engineered judgments that we use. The mullion can pass in front of the slab, or it can stop and start. So when we started going multi-story, we started smaller, lower level buildings, and we worked our way up taller and taller as time went on. So this is an example of a 8-story facade in Chicago. It also has the faceted wall as a feature. So all the fire safing and the slab intersection with this facade was all worked out with the architect. And we won this commission because our system does not need a member at the fold line. This is the modification to the mullion that we made to accommodate the thing. And the architect here, he pulled the VS-1 system into all the interior glazing, and you see how thin and minimal the aesthetic is of the system. This project is under construction right now in Dhaka. It's a 14-story building, and it has a twisted geometry. We were selected to build this facade. We are right now attaching the anchors and the mullions. And this project uses a innovative concept called cold bending, where you take a flat piece of glass and you distort it, you bend it in the field. So the cost of the glass is like any other building. So if you took any panel off this building and laid it on a flat table, the one corner would be off the table by 135 millimeters. We did all the engineering and testing to achieve this. This is a mock-up over here of the bent panel. We were able to deflect the glass by hand, but you see the system components are exactly the same as if this wall was a flat wall. So the major cost impact on a project like this is mainly the structure, the building structure. You have to vary each floor slab from the one below. But as from the facade system, it is not that much more expensive to do this level of creativity as opposed to a flat box. And that opens up iconic opportunities for developers to invest in a slight premium as opposed to double or triple the cost of a normal building. Cavity walls, we have done several projects. This is one in Chicago. It's a 10-story building. It has a 1 meter deep dual wall. It is connected to the building control system. It's vented on the sides going up, and it provides a super insulating characteristic to that portion of the building, and it also provides complete acoustic isolation from the city. Also, you can see how transparent it is. You're looking through two walls here. Accessories. I remember hearing a lot of complaints by architects at meetings in the early 2000s of how they were asking a curtain wall system to do more than it was conceived when in the 50s. So solar management systems were needed, and so we responded to that by enabling the VS-1 system to have these components, these accessories as part of the system. They attach to the system. You don't have to make a separation and have a separate system on the outside that ties into the slabs. This is actually part of our curtain wall system. This is a 6-story building in Long Island. It's a university building, and all of these components were made to be part of the system. Should your building call for a real, statement of something like this, we have a version of our system that can accommodate this kind of a facade. This is a Central Bank of Ireland in Dublin. It shows the ability to use a triangular pattern in the facade system. This is a rhombic grid system. And then we're starting to go a little taller. This is the Marriott headquarters in Chicago. It's a Marriott headquarter hotel. Our typical glass corner is an all glass corner. There's only a stainless steel rod. Structurally, it's glazed at the corner to transfer the loads. This shows the ability of the system to go up from glass to perforated panels, and then the integration of perforated solar fins to the outside, anywhere you want them on the facade. Now we're going a little higher. This is the HQ 460 building. It's very close to where we are right now. It was the first higher-rise building we did in India, and you see the mullions are to the outside on this building. We have operable windows in it as part of the system, and then this is also here in Mumbai. We are actually finishing this building right now. It's the Arihant building. And we have a glazing crew from the United States that is participating in putting the final seal on this building using modern caulking techniques. There are actually two buildings. This is a collaboration with Gene Gang in Chicago. It's a 100-story building. We're involved right now in this portion of the building, which is the lower level. It's a 5-star hotel and restaurant at the bottom with a 42-foot span. We developed this two-way grid because the architect had designed a very unique, iconic exoskeleton, and we made modifications to our system to accommodate that. And the original design of this tower facade was using the VS-1 system. And what Jean Gang did was she took full advantage of what you can do with the system, where she varied the grid. And so if you study the geometry of the facade, each floor is different than the floor below. And you simply cannot do that with a unitized strategy. It would destroy the economics of a unitized wall. And we don't even feel that. It doesn't matter with our system. So we made a study of one of the typical floors, and the way we solved this was we created a scallop in the facade. So there's a step at every floor, and you notice there are no operable vents in this solution because, and of course, we had our features of the system is all glass corners, very minimal glazing system, but on the underside of this edge, which is all part of our solution for this approach, we built in a sill vent, which is passively operated. You set the temperature that you want this vent to open at, and it opens automatically without any electricity. It's a thermal spring that operates it. If you want to, quote unquote, open the window, you can override that by just pulling a latch up and moving it. This is the last project I'll leave you with, and this type of design strategy can be applied to tall buildings as well. This is a project in Chicago for Loyola University. Now on the west wall, it has a dual wall, and it's an extreme. It's a 2.5 meter airspace, 3-story building with a extension of the facade above the roof line, and it's vented at the bottom, it's vented at the top, the inner wall is vented, and the opposing wall on the other side is vented. The slab is cooled or heated. You see that by the coloring. So you have a natural mode, a hybrid mode, a cooling mode, and a heating mode. And the goal of this building is zero energy. It's to use the sun in the winter to have a pleasant interior temperature environment, and the heat is off. And the same in the summer. That's the goal, and they have achieved it several times. So it's extremely innovative. It was a pleasure to be involved with this. The HVAC consultant was Transolar in Stuttgart. These are the windows at the top venting. These are the windows on the opposing wall. And here the shades are deployed. There are blinds inside the airspace. There are 3 lines of blinds. So this is what it looks like inside when the blinds are deployed. Here the blinds are up, but you can see the housing of the blinds. And up on top is the lantern, they called it, where the back venting is to vent the top of the wall. And then here is a picture where the blinds are retracted into their housing. And you can see the vent grill below at the base of the wall. So that is how the system is conceived. That is a VS-1 wall. The outer wall is a cable net. The inner VS-1 wall has vents that are hooked to the control system, and the vents on the... This is the wall looking east over Lake Michigan. And that concludes our presentation. Thank you very much.
Thank you, Frank, for that inspiring note.